Hello and welcome to another tutorial. We are going to continue our discussion on classes. We looked at the static fields or static state of the classes and then static methods. The takeaway from static methods was that you don't have access to the non-static state of the object in the static context like static methods. And then we said that a static method cannot refer to this keyword because in programming languages or in object-oriented programming languages like Java and C++, this keyword is implicitly passed to every non-static method. For example, if I have a static method, this is basically actually what happens here is that this method is get x behind the scenes at runtime. JVM assumes that there is this pointer, and then there are other parameters that are formally passed to the method itself, right? So this is implicitly passed to the non-static methods. So for non-static method, and the reason we need this because we can have, when you say something like return x and x is a non-static field, what actually happens is that JVM does this.x, right? So the reason that we can use x directly, non-static field directly with their name, is because actually behind the scenes there is this reference in C++. I said this before. This is a pointer that points to where the state of this object is. In Java, we don't say pointer, we say reference, but that's the same story. Basically, JVM needs to know where this x variable is stored, right? The value that, remember, variables, the name of the variable doesn't mean anything. This just means there is some memory location that holds the data that this variable holds, right? And when we say return x, JVM needs to know where to locate this x. And that's why we have this, because when you call the constructor of an object to create an instance of that class, what happens here is that this pointer now pointing, we said that when you call the constructor using the new operator, you allocate some memory in the Java heap, and that memory holds all these fields and values, right? If you have multiple non-static fields, some non-static state, that you get a pointer when you call the new operator. Pointer points to where those data are stored in the Java heap, and every object also stores that memory location internally in this location. So when you say return x, the JVM, or in C++ the compiler, in the actual after the compilation, what happens here is that basically in C++ it's equivalent to dereference this and then access x, or this arrow operator x, for example, right? It means go to this memory location and then from that location locate x, because when you have a state, obviously if you have multiple ones, this pointer is pointing to the start of that memory location that holds all the fields, and every field based on the size has some offset. We know that int is 8 bytes, for example, 4 bytes, right? 32 bits. If I have double y equals 10, then if, for example, I mean, in Java, it's not clear what happens, but let's say if one assumption, one scenario, a simple scenario is like this, that this pointer is points to the x, the location of x points to location of x variable, and then if we want to access y variable, then we offset x by the size of x, right? Size of x. If there is a flat layout, I mean, in Java obviously there is no flat layout, there are some headers and stuff. In C++, typically there is a flat layout for the classes. So if you know the address of the object actually points to the first non-static member, that's usually the case in C++ for the flat layout structures or classes. And then so size of x in this case is 4 byte, and this is a pointer, 64 bit, right? It's a memory location of the first element, which is x. If we offset it by 4 byte, we move to the next location, which is now y, and if we dereference this, we get y, right? So basically if we dereference this, we get x, right? That's where the this points to the first memory, the first variable, and then dereference. And again, in Java, all this complexity is hidden behind the scenes. You don't need to worry about this kind of stuff, but this is the philosophy of having this. So when you create a new operator, it returns when you call the new operator, it returns a pointer to you or a reference to you in Java where that the state of that object is, the data that that object holds. But then internally, each object also saves this memory location, because if you have a non-static method, you want to access some of the variables, some of the non-static state, you have to, behind the scenes, this pointer is used to access those, right? And this is the general theme. Obviously in Java, there is no, it depends on the implementation. Various vendors can have different implementations for how this works, as long as everybody adheres to the Java language specifications. But in C++, because the compiler has to compile to the machine code, it's just the CPU, hey, go to this memory location, get the value at that memory location, and basically read it, bring it into some registers. So in C++, because you compile directly to the machine code, then you have to talk to the CPU, and CPU only understands registers, memory locations. So this is actually what happens in C++, right? This is definitely a memory location. In JVM, in Java, things could be different based on the implementation. All right, so in a static context, you don't have access to this because this is the memory location for the non-static state. And we said that when you call the new operator, this is a variable that is initialized and stored in the object. But then when you call the new operator, it only allocates memory for the non-static part of the state of the object. So the static part is stored somewhere else way before you call the new operator. It's created and stored when the JVM loads the class file into memory. So it makes sense that in the static methods, you don't have access to this. You are not allowed to use the non-static part because these are supposed to be separate. Constants, we've already seen this. Static final variables are CompileTime constants, which means whenever you use this symbol in your source code, if it's a static final, the compiler will always replace this with the number in the bytecode. So in the bytecode, there is no extra bytecode to say, hey, load the value of this variable. There is no variable. In the actual bytecode, there is this number. So this symbol and this number become synonymous with each other, right? So the static modifier in combination with the final modifier is also used to define constants. The final modifier indicates that the value of this field cannot change, right? And we said that if it's not a static, if it's just a final double pi, what this means is that it doesn't enforce you to initialize it right away, because now this is part of the non-static state of the class. So you can defer the initialization until somebody creates an object, until somebody calls the constructor, and then you are forced to initialize this variable in the constructor. That's part of the contract of the final, which means if this is not a static, if somebody creates an object, this value has to be initialized. So the only place to initialize it in the constructor. If you have multiple constructors, you have to initialize, make sure that this variable is initialized in all the constructors. Okay. But then, so if a final variable is not a static, you can defer the initialization to the constructor of the object. But if it becomes a static, now you cannot defer the initialization. You have to in the same line of code that you say a static final double pi, you have to have the equal something. This is mandatory. If you don't do this, the compiler refuses to compile your code, right? So as soon as you say a static final some variable, you have to say equal something. Then it becomes a compile time constant, right? You cannot defer the initialization of the static final variable. That's just because the only place that you can defer the initialization is to the constructor. But if it's a static, somebody might not decide. A static means you don't need to call the new operator. You don't need to create a new object. So if therefore the compiler says that, okay, maybe somebody just directly wants to access and read this variable, if you haven't initialized it when you declared it, then that doesn't make any sense. All right, so I hope you understand why a static final variable has to always be initialized right away. You cannot defer its initialization, and we've seen this before, right? So if I say public static final double pi, but I don't initialize it, this means I'm deferring the initialization to someplace else. And obviously, because this is final, it means it's going to be in the constructor, but the compiler doesn't allow me. And the compilation error here is that the blank final field pi may not have been initialized, right? So the compiler gives me this error just because this is a static. If I remove this static, now I don't get a compilation on this variable, but I get a compilation on the class itself, because now I'm deferring. I'm allowed to defer the initialization, but it doesn't mean that I can't, but then it means that I have to initialize it anyways, and that's why I get a compilation error on the constructor. It says the blank final field pi may not have been initialized, right? So if you have a final field that is not a static, you can defer the initialization to the constructor, right? That's the maximum point that you can defer it. You have to initialize it to the constructor, right? Otherwise the compiler won't allow you. But as soon as you say it's also a static, now you're not even allowed to defer the initialization to the constructor, because static fields don't really care about the constructors. Static final fields have to be initialized right away, because somebody might want to access this variable without creating an object, because a static state, it doesn't depend on the state of a particular object. So for example, the following variable declaration defines a constant named pi whose value is approximation of pi, the ratio of circumference of a circle to its diameter. Constants defined in this way cannot be reassigned because they're final, and it is a compile time error if your program tries to do so, right? You cannot change the value of a final variable after it's initialized. So by convention, the names of constant values are spelled in uppercase letters. If the name is composed of more than one word, the words are separated by an underscore. All right. So this is a convention. Please always stick to this convention, because this has been used for many years. Even in other programming languages like C++, this convention, I've seen this, some people use it, which is a very nice convention. All caps letters and then separated by underscore. We saw that, for example, electron charge here. And then basically, and then we rely on basically IDE's autocomplete. So if I say electron charge, just type a few letters. I don't need to write the entire thing, just a few letters, and then hit enter, and then the autocomplete of your IDE does the rest, right? Which is a very nice feature to have. So one thing that I want to mention is that there is something called magic numbers. So let's write it here. Magic numbers in your code, and the best practice is to avoid them, which means that when we say avoid magic numbers, means try to extract them as constant variables or compile time constants variables. Compile time constant variables. What this means is that, let's say instead of having this, let's comment this out, and we get error somewhere. Instead of trying to have this variable as pi, let's say I just say 13. I know the value of pi, maybe it was here. Let's just read it, and then let's replace this with here. Yeah, so this code works, and it's fine. The problem is that if somebody looks at the source code, they might not know what this number means, because there is no name associated with this number, right? If somebody doesn't know that this is pi, the value of the pi, which is a mathematical constant, then they don't know what this, and these are called magic numbers. So so at the moment, this is a magic number, or a hard-coded number, hard-coded literal, right? I mean, the idea is to try to avoid this, and your IDE provides some very nice refactoring tools. For example, in Eclipse, I'm going to right-click, you select the number, right-click, source, or refactor, and then in the refactor, we have the option, let's see, extract constant, right? So you select that number, refactor, extract constant, and what this does is it tells you, okay, I saw this number, 3, 4, 5 something, and then what's the name of the constant? We want to say pi. What kind of access modifier? Let's say this is a constant, compile time constant. Let's make it public, right? public static final double pi. As soon as you say it's constant, Eclipse knows that you want to declare it as a static final. That's the meaning of constant in Java, right? And then Eclipse knows that it has to put it in the scope of this class. So now where is the pi? It puts it at the type. So the way Eclipse works is it puts the static state before the non-static state, right? We can move it back here, for example. Okay, so you can make it public or private, doesn't matter. Private just means nobody else, no other class can use this constant, but it's still a compile time constant. All right, so try avoid using magic numbers and just right click on them and then extract. For example, 5.1 here, nobody knows what this is, right? This could be have some meaning, this could be some physical constant. So I just right click, refactor, extract constant, and then let's call it and then all caps, some physical constant, right? All caps, underscore, separate different words, and then Eclipse, I chose private, but I could also choose public. And again, this doesn't change the bytecode at all, because it does change a little bit because you're declaring a static variable, but it doesn't change the bytecode of this method, for example, because at compile time this variable is going to be replaced with the number, right? So really the bytecode of the method doesn't change. What changes is the readability of the code. And the other thing is that if you're using constants, it makes sense to make them available to everybody, because maybe somebody else uses your library and they want to use this constant for something else. They don't have access to your source code, right? Because when you build your project, create your library, it's just the bytecode and nobody looks inside the bytecode, right? So instead you make it a constant, and then this is still available in the bytecode. So people can say constants dot some physical constant, right? And then they immediately have access to this constant. So try to extract all the magic numbers from your methods and then define them as compile time constant. If it makes sense to make them available to everybody, define them as public, otherwise protected or private. Now protected doesn't mean something. The only meaning here for protected is that if you want somebody to subclass it and have access to this. But then the thing here is that usually utility classes that all the state is static, you don't want anybody to basically subclass them. So here I'm going to declare it as public. It's also allowed to be just package level access. So this constant is only available to the classes in this same package. Sometimes this makes sense, but almost 95% of the time I would say the compile time constants are public, because really you don't care if somebody accesses this. They can never change the value of this number. They can only read it. So these are read only values, read only variables, and because you don't put them in the global scope. So in this case it's a positive thing that Java doesn't allow global scope, because you put it in this class, it doesn't pollute the namespace, or basically there is no global scope. But for example in C++, if you have lots of constants, they just pollute your global namespace, right? But here you put it here, even if it's public, you still need to say constants dot this variable, and that's fine. I mean, you don't worry about anything. So usually in Java at least every compile time constant is public. Okay, note, if a primitive type or a string is defined as a constant and the value is known at compile time, the compiler replaces the constant name everywhere in the code with its value, right? So primitive or a string. Now this is another thing about constants that we need to talk about. What happens if this variable, which is a static final, is not a primitive? What happens? Does it still work? The compiler replaces? What's going on? Because then it becomes a pointer or reference, right? Here, obviously, what we're seeing here is that if it's a primitive or a string, then it's going to replace at compile time. This is called a compile time constant. If the value of the constant in the outside world changes, for example, if it is legislated that pi actually should be this, you will need to recompile any classes that use this constant to get the current value. Basically, what this means, again, if it's a primitive type, so primitive type, or a string. So I think this was later added, a strings. The reason a strings also work because it's a final class and it's part of the JDK. So JVM knows that this class, a string, can never be subclassed and its value never changes, right? That's why it's also allowed to basically replace the string. So let's see what happens. We already know that if I look at the bytecode in the util package, let's look at the constants class. Let's look at the class file viewer. All right, let's see what happens. So in the sum value method, let's zoom in. Now, as you can see, we are loading a void variable which is double 5.1, and then we return return a double, right? So this value has been replaced with the 5.1, which is we expect. The reason that the bytecode is a bit weird, it's a wide load because a stack of a method in Java, unfortunately, is 32-bit. So you have to when you want to load a 64-bit variable, you have to load it in the 2 slots of the stack frame, right? It happens in 2 instructions. LDC2 means load a constant which is wide, which is twice as wide as a slot of a stack frame, right? So you see, that's why it says that this stack is basically 2. The reason is that, first of all, this is a static method, so it doesn't take this. It doesn't take this variable. So 2 just means this 2 is 2 slots occupied by this 64-bit. If I make it non-static and save, Eclipse immediately recompiles, and then actually we have an error here. Okay, some value is okay. We're using that somewhere, so let's not make it static. But the idea is that if it's non-static, then or I can make it. Okay, at the moment I cannot make it non-static, but let's say private double some value number 2 and return some physical constant. All right, so this is kind of like a non-static version of this, and then let's look at this some value number 2, and then as you can see, we are loading that. We are loading the 5.1, and then we are returning it, right? So this is at index 0, and then the type is constant. So there is a local variable on this method, which is this pointer at index 0, and then we are loading basically 2 values. Okay, so let's remove this. All right, back to where is that sum value. So we are loading this, and then now what we want to see is what happens. Let's go back here. All right, what happens to the strings? So we already know that for the basically primitive types, if there are a static final, the compiler will replace them. What if so let's create another one. So private static string get value, and then return so let's go ahead and create a CompileTime constant public static final. Now it's a string type, and remember, a string is not a primitive type. str, let's call it hello. Okay, and let's make sure that this string comes from Java lang, and then we're going to return str. Okay, and now I'm going to save it. Eclipse is going to recompile, and let's see what happens to the get value. Now as you see, what happens here is that now we are just loading the hello string directly. We are not returning a reference or something, right? And another thing is that the way Eclipse does this, so let's change the name, hello str. Okay, so hello str static final, and as soon as I save and Eclipse compiles, you see we're just loading the string itself. So even for the strings, which are non-primitive types, still the concept of the CompileTime constant works. But unfortunately, this doesn't work for any type of other reference type. So a string is the only reference type that works, because you have to initialize it to the literal. Because for primitive types, we do have literals. For strings, we also have literals. That's why you are allowed to do it. For any other types, you kind of need to call the new operator, right? Public static final, let's say bicycle, and then my bicycle. Eclipse already knows that, and then we have to do something here, right? Because if you do this, you are not initializing it. Initialization of object means you have to call the new operator, right? So bicycle, and then we can use this constructor 1 2 3 for example. So this is still works. We are defining a static final, and then we have to initialize it. If it's of a reference type, it means you have to call the new operator. That's how you initialize a reference type that is non-static. If it was a string, you have a literal. For reference types other than a string, you don't have any literal, so the only way to initialize it is you call the new operator. And then what happens here is that so let's say private static bicycle, get bicycle for example, and then we're going to return my bicycle. All right, now let's look at the bytecode. Get value, get bicycle. Let's see what happens. Here it says get a static field dev util constant my bicycle, which is of type bicycle. What this means is that there was no way for the compiler to replace this reference type with some compile time constant. All the compiler can do is, hey, go and then read this static field. This is different. So reading a static field is different from replacing it with the actual value, right? So it says that just go and read it. So there is no benefit of defining this other than maybe we want to make this available before even creating any instance of this class. Otherwise, the compile time constant concept doesn't really apply here, because the compiler cannot replace this with something, right? Because the only thing that it can replace it with the actual object, but it doesn't have any meaning. It is a pointer, so it just says go ahead and read the value that this holds. So the reading the value is deferred to the execution time, or when JVM actually somebody calls this method, and then JVM goes back to searches for this variable and then sees that, okay, it's pointing to this object. JVM knows where this object is in the Java heap, so it knows to go back and return it, right? So the compile time constant concept only applies to the types of variable that you have some literal. You can initialize them with literals. And for strings, even though it's a reference type, we know that there is a string literal, so we can use. For other types of references, we cannot do anything. There is no literal except to use the new operator to initialize them. So I hope you really enjoyed this lecture. Have a good understanding of compile time constants, why we use them, what's the benefit, how to extract a magic number to a compile time constant, which is one of the best practices. Please stay tuned, and I'll see you in the next one.